Hello and welcome back. In this video, we're going to take a quick look at the physics of the guitar. Now, this video is meant to be kind of a high-level overview, and certainly is not all-encompassing, but I want to get you introduced to a couple concepts that will be useful to know when kind of deploying or developing software for guitar effect processing. So we're going to look a little bit at the physics and kind of get an understanding of what kind of data converter do we need to, be able to accurately capture a guitar. So it sounds good. So you see my picture here. I have a guitar. This is a Carvin Bolt T, just a stock picture. So just so you know, in case you didn't know what they were called, this is called the bridge here. This up here is called the nut. And you notice an electric guitar, we just have, the bridge and the nut are kind of, points of zero motion. And then for the string is allowed to vibrate in between. We have pickups, picking up sound. Now, most pickups in guitar are electromagnetic. They are just, I'll just draw it as a coil. So what happens is that you get a disturbance in the magnetic field due to this, change, the velocity, the rate of change of position of the string. So what happens is that you essentially are inducing a current in this coil that is kind of proportional to velocity. The velocity of the string, not the position, it's velocity. So that's how electromagnetic pickup works in a nutshell. The string wiggles, disturbs a magnetic field set up by a permanent magnet inside of the coil. We get an induced current. You can use Maxwell's equations to kind of work it all out. And then we get a tone. So there's a couple of things that kind of control how a guitar sounds. So what we're going to look at is some of the basic physics of how a guitar string vibrates. And then we can kind of understand, how the pickups affect the sound and kind of use that to figure out what kind of data converter requirements we have. All right, so here we have, this is, an equation that kind of governs, the motion of a string in one dimension. So what this kind of tells us here, this is what's called a partial differential equation. It relates the second order derivative of change in the displacement of a string. So I'm just going to draw a string right here. So the displacement, we'll kind of draw it like that. The second derivative, which is really the acceleration, to the second derivative, of the shape of the string. So this is really a shape-based term, or first derivative so give us slope. Second, this actually tells us more about the shape. So it's related by c squared. So this is the common what's called wave equation. So it kind of relates the curvature of the string at any point to its acceleration. Now this is valid for small string displacement. As it turns out, it works pretty well. Now even for large string displacements, that'll just kind of affect the frequency of where the string will vibrate given the length. But it's useful for us to understand how string vibrates. Now, if you have a course in partial differential equations, you learn that the wave equation, it's pretty neat. Here's how it's solved. Back in like the 1700s, they figured out, here was the solution. Basically, it said that any function with respect to x and t, all right, any two sets of functions, with these arguments in the middle, you add them up, that solves the wave equation. Now you say, what in the world does that mean? Any two functions, like the log function, also says, yeah, that is true. It turns out that's any two waves traveling in opposite directions. Now, this is only true for, that is the general solution to this differential equation. And that makes an assumption that there's no, what are called boundary conditions. Well, we have such boundary conditions. We have a string that is fixed here and here, all right, at the nut in the bridge. So we don't have any function. We have to find functions that the displacement is 0 at the nut in the bridge. So let's go down here a little bit. And, well, what I can imagine, if I have my bridge over here at x equals 0 and the nut at x equals L, I could kind of draw a shape, that kind of moves up, kind of like so. It starts, at 0 at the bridge, moves up, and goes back down. And so this is a solution. It turns out this really is a solution to that differential equation. But differential equations are funny, especially partial differential equations, in that with a little more imagination, you can say, wait a minute, I can think of even more solutions to that differential equation. Like, as long as the motion is 0 at either end, I can do this. I could take a hump that goes up and down. I could go up, down, and back up, or I could fill it in like this. So, it turns out that these are just sine waves. All right, you can model this. This is 1/2 sine wave. The one in the middle is a full sine wave from 0 to 2 pi. This is 3/2. And we could go on to infinity here. We could put 1 billion cycles in here, and that is a solution. Now, the question is, what about a shape like this? Because this looks a little more realistic about if I have the bridge here, and if I'm going to pluck the string, and imagine I kind of pull it up and it kind of takes this shape like this. This certainly is a solution, but how does it relate to these solutions? Well, it relates this way. It turns out that if we take each one of these shapes, multiply them by a coefficient, and add them together, we can make any other shape. So what that means is that this shape can be written as the sum of these shapes. So these shapes are what are called the normal modes. They are the natural modes at which the string will vibrate, but we can form any other shape from those normal modes. So no matter how you pluck or pick the string, they are formed from these normal modes, where this is the fundamental mode, this is the first mode, second. Another way to think about this is the fundamental mode. The one in the middle is the first harmonic. This is the second harmonic. They're all valid solutions of how a wave can appear on the string. So how do we write that? So this is kind of the mathy approach of how we write that. So in the middle, we have sine. All right, that makes sense. We need a sine wave. All right, we need our coefficients in front of the sine. Well, the next part is we need something that at x equals 0, the function is 0, and that's sine. But when x equals L, we're at 0 as well. So if we take x divided by L, when x is L, this whole term's 0, and then we put this n pi to get our half wave in there, and that's all there is to it. We have these sine waves. These are indices for our harmonics, and we just sum them up. Now, this whole term here is just a mathy way of writing the sum of these shapes. Now, one thing I kind of conveniently left out is imagine these are the shape of the string as if you're to freeze frame in time. So if you plucked a string and it was vibrating and freeze frame it, you could see any one of these shapes or some of them. This represents like the maximum amplitude at any little point. Well, this string, it has to move. The middle point, has to go, down and back up and down and back up. This goes down and back up, vice versa. The difference is this point on the end, its amplitude is smaller than this one. So this shape is kind of showing the maximum swing of that string. Well, to represent what's called the time varying part, in engineering land, we like complex exponentials. So really, this is just a way of saying sine 2 pi frequency times time, where this part here is describing the spatial shape of the string. This part says it wiggles over time. So this is a shape along the string, and then this term here is special in that is the amplitude of the string harmonics. What controls that amplitude? Well, that's controlled by how you pluck the string. You'll get different harmonics if you pluck it near the middle versus at the bridge, and that's just kind of common sense. You've kind of played with a guitar, and that's just how it works. But you've seen in quick nutshell, mathematically speaking, this is the math, and that's the math to describe it. So those different sounds, that's created by the amplitude of the harmonic. So yeah, like I said, the e to the j omega t is the string wiggling over time. Now, let's do this. Let's put a bridge position pickup. So if we were to pick up, the variation of the amplitude, the string wiggling, if I put it at the bridge, I'm going to set it out just a little bit out here. And let's draw the first three harmonics. Notice that it only picks up the first harmonic at less than 50% amplitude. So if here's like 100%, here's 50%, it's only picking up the first harmonic, a little bit. But the second I should say the first mode, the first harmonic, which is here, or first harmonic, notice it's actually, the amplitude is almost at its peak. It's almost picking up all that, where it's picking up 100% of the third. So at the bridge position, it's actually picking up more of what we'll call the high frequency harmonics than the low frequency, and that kind of makes sense. You can listen to a bridge, and there's definitely some brightness there. Now, what happens if we switch to the neck pickup? Well, the neck pickup is further up the string. Notice how it picks up the amplitude, almost 100% amplitude of the fundamental mode, but almost nothing of the first harmonic and quite a bit of the second, but it's inverted. All right, so that's why a neck and a bridge position sound different. They're picking up different harmonics along that string. Now, here is the absolute reality, is that a pickup is not a point source. It's sensing velocity of the string, but it does it over an area. The pickup integrates the amplitude over a large area of the string. Now, this is very important. So what I'll show you here is this kind of shows the neck pickup response of just the position of the pickup over time. That because it integrates, it picks up this red bar, and we get peaks and nulls in the frequency response. So that's just a way of showing that, yes, the changing the pickup position changes the sound. Now, here's the first step in kind of figuring out, well, how fast do I need to sample to a guitar pickup to accurately pick up what's going on the electric guitar. So let me do this. Let me get a blank screen. Actually, I don't even need a blank screen. Let's start here. Let me get this one here. It turns out that the fundamental frequency, all right, so the fundamental frequency of the low E string, let's say this is low E, if you work it out based upon the length and the tension of the string, it's approximately 82 hertz, 82 cycles per second, which is slower than most people think. It's pretty low. Bass guitar, it's about 41 for the low E. Now, if that's the low E string, let's go to the next harmonic. This is up at the 12th fret, just double it. It's roughly 164 hertz. Now the high E string, roughly double that, not roughly, but roughly 329 hertz. All right. So you notice from low E to high E, we're still not that high in frequency. So let's keep going. If we want to go to high E on like the 12th fret, that is about 660 hertz. And let's go 24th fret, high E string, is about 1.3 kilohertz. All right. So that's the frequency of the whole guitar. Now on the high E string, you can still get sounds out of it higher, but let me show you something. Let's go back to a picture of the guitar. Give me 1 second here. And this is a 22 fret guitar, but 24 fret is about right here. So this is about the wavelength right here at the 24th fret. All right, we double the frequency. All right, this is about the wavelength. So that puts us, at about 2.4 kilohertz. And then we can double it. We got about 4.5. But one thing I wanted to mention is that the higher you go in frequency, even if there's multiple harmonics above that 24th fret, because the pickup integrates over a somewhat large area, if your pickup is on the same order of magnitude as the wavelength of the tone, that integral, evaluates to approximately 0. So the pickup itself, its response around 3 kilohertz tends to get, there's a small resonance due to some internal stuff going on in the pickup. But then it really rolls off the response, not only because of the response of the coil in the pickup, but just the physics of how the pickup integrates the string, integrates that velocity over the string. So what I want you to take away from here, I'll just go like this. At about 4 kilohertz, I'll put it right there. I'll put a rough order of magnitude, 4 kilohertz. That's about it. That's where the guitar ends. Once you get so high up, this is way, this is a couple octaves higher, even than the 24 fret on the high E string. Everything starts to roll off. So this is kind of the limit. And that's actually pretty surprising to people. They think you need all of this frequency response in the guitar. An electric guitar, it's really not. Now on acoustic guitar, there's other things going on, string noise, and there's other stuff that's higher than that. But for an electric guitar, it's a low frequency instrument. This is where it rolls off. So the next question, is if we were to design something, a signal processing system for the guitar. Let me get a blank slide here. If we were to design a signal processing system for this guitar, here's the question. What do we want for a sample rate? We have this Nyquist criterion. And so do we do CD quality, CD quality, they say 44.1 kilohertz. Do we go to a more popular 48 kilohertz? You get the audiophiles who say we want 96 kilohertz. Or the super crazy people, hey, well, what about 192 kilohertz? That's seems to be the new thing. Well, I say no. This is all kind of dumb. You aren't doing anything by sampling that fast because from a sensing system, it's just not there. There's nothing there. After playing around, I think for about 24 kilohertz sample rate, you're good. You don't really need to go any faster than that. Everything above that is really just a waste in computational power because, everything kind of rolls off around 4 kilohertz. You always, when you sample, want some, guard region for your anti-aliasing filters. So beyond that, you're done. So 24 kilohertz, that is more than adequate to cover the entire range of that guitar. You get several, points, even the highest frequency. Even if you had some really narrow pickups, which really wouldn't pick up much to begin with, you're not going to see much above that. So I'd make the contention that 24 kilohertz is all you need. Now, if you really cared, you could do it at 44.1, but it turns out that doesn't matter. Above that, it's been scientifically proven that sample rates above that are meaningless. There are audiophiles who will disagree. But there are some papers, and let me go find you one. So there was a double-blind study done by some groups published in the AES that basically took, 24-bit, 96 kilohertz, very high sample rate audio and rammed it through a 16-bit 44.1 kilohertz, what they call bottleneck. Long story short, in a double-blind study, audiophiles could not tell the difference. So sorry, audiophiles, you're full of crap. But for the guitar, we don't even need to go that high. So because there's really nothing there. So I'd argue 24 kilohertz is good enough. So that brings us to the next question. So what I have here is a picture of the ISO 226 loudness curves, and what they show, they basically show that the ear is a very crappy sensor. The ear, depending on frequency and sound pressure level, the sensitivity of your ear is all over the place. So what it shows you is over time, we have all these curves in red, where the bottom one here in red shows the threshold of hearing and the sound pressure level in dB SPL. So way at the low end of the frequency, we got to get up to like 75 dB before we hear anything. And then even when we get to 100 hertz, we're at 25. And so you can kind of look at the difference between the threshold of hearing, and this curve is the threshold of pain when your ears start bleeding. So if you really want your ears to bleed, look at this. So at 100 hertz, that low E string, we got about 105, down to 25. We have 80 dB of dynamic range that the ear can cover, and that's from you can't hear it to your ears are bleeding. So what that really means is 65, 70 dB is just fine. Now, the most sensitive part is in this 3 to 4 kilohertz, where ear is a very good sensor, and there you have about 120 dB of dynamic range. Now, saying 120 dB, once again, that is all the way from barely audible to your ears bleeding and your brain leaking out the side of your head, and your hair's on fire. So do you need 120 dB? Absolutely not. So the question is, what do you pick? Well, it turns out in some ways it doesn't matter. For an electromagnetic pickup, you only get your signal to noise ratio. Pickups are horrible. 60 dB is about a good one. In a good measurement test with actual cables that people use, 60 to 70 dB. Now we want to do better than that. The first thing is I say 80 dB is adequate to cover everything you want to hear based upon those curves. So, which at the lowest level, that a 12-bit converter can get us that. Now, what that means is, though, 12-bit is certainly good enough, but that means whenever you measure your signal, that signal better span the entire range of your data converter. So, while that's good enough, we can do better. So 16-bit is certainly sufficient. That covers everything. That has about a 96 dB signal-noise ratio. That covers human hearing up until about the threshold of pain over most audio sources. Now, the MonkeyJam, only because I could, and it didn't really cost me any more, I went with a 24-bit Wolfson converter. Now, it turns out that the actual signal-to-noise ratio in that converter, because it's low cost, is about 90 to 95 dB, so it's effectively a 16-bit converter, which is good enough. The only advantage that 24-bit gives you has nothing to do with how good it's going to sound, is that you can get a little bit more sloppy on your input range, so you can provide kind of a small signal. You might not have to gain it up, so you can adequately get the whole signal without clipping. But 12-bit for a guitar, at about 80 dB is more than enough. It's sufficient, but you got to make sure your input signal spans the range of the converter. 16-bit is gold, and the only reason you go to 24 is because getting a 24-bit converter doesn't really cost you anything in terms of price. Data converters are 24-bit, but to me, what really affects your computational horsepower, computational load, is sampling frequency. I argue 24 kilohertz is just fine. You can say I'm wrong, but I tell you what, go waste your own CPU cycles. You can't tell the difference, and I'd be willing to bet that if you were to take a double-blind test, you would hear no difference. Now, here's kind of like the last part I'm going to point out here. Let's go to this little picture of the amp. So if we're trying to model like an amplifier, here is the absolute other reality. Let's say there is stuff up at 4 and 6 kilohertz or whatever, and you want to go higher. it doesn't matter. Look at a 12-inch Celestion speaker. They roll off at 3 kilohertz. So when you model a speaker between anywhere between 2 and 4 kilohertz, you know, having a sample rate of 48 kilohertz or 96 kilohertz is just dumb. Because if you're modeling the speaker, you don't need all of that bandwidth because the speaker doesn't represent it. So if you're trying to get a tone that sounds like a Fender or a Marshall, you know, 24, I'm saying 24 kilohertz is just fine, and you'll have lots of CPU overhead, you know, to spare. It's not going to hurt anything. So, all right. So I hope this video is informative. Now, one thing, a disclaimer: acoustic guitars are a little different animal. There are you do need some additional data converter horsepower, only because you're not limited by the pickup. That you're hearing almost everything that string is doing in air. And even if you use a piezo pickups, you know, their response will go really, really high. Now, so you want to pick up all that really crispy stuff in an acoustic guitar. So that I could say, yes, sample that at 44.1 or 48 kilohertz. That would make sense. But electric guitar, no way. It's a low frequency instrument. So, all right. So this gives you some of the background of, you know, kind of how things were chosen for the MonkeyJam. And so maybe you understand a little bit more about how guitar and guitar pickups work. At least gives you enough information to get started to maybe look up a little more on the internet. So I will see you later.